Hey yo, welcome to Astronaut. Today we're discussing different theories for the shape of the universe and what each theory implies.
I feel like an astronaut in what you know about rolling down in the deep.
Number 1. The flat universe. A flat universe obeys Euclidean geometry and is most obviously illustrated as a plane. Objects that move parallel to one another continue to move in parallel directions. Number 2. The hypersphere. A spherical universe is a positively curved, closed space. This theory suggests that the universe will contract until it reaches a point also known as the Big Crunch. Objects that move parallel to one another in a positively curved space eventually converge. Number 3. The saddle. A hyperbolic universe is one that is negatively curved and open. Objects that move parallel to one another in a negatively curved space diverge. Are these the only 3 theories? Definitely not. People have postulated many other ideas for the shape of the universe, such as a horn, another example of a negatively curved space, or a ring torus, in which a flat plane revolves tangentially around a circle, forming a donut-like shape. But these 3 theories highlight how the curvature of the universe affects its geometry and outcome. If we were to draw a triangle in each one of these universes, the angles in a flat universe would add up to 180 degrees, or, in radians, pi. In a positively curved space, the sum of the angles would be more than pi by an additional factor of a, the area of the triangle, over r, the radius of the curvature, squared. In a negatively curved space, we would subtract this factor. To generalize this, we can say that our angles, alpha, beta, and gamma, equal pi plus a curvature k times the area of the triangle divided by the radius of the curvature, squared. The curvature k is equal to 0 in a flat universe, meaning there is no curvature at all. In a positively curved universe, k is greater than 0. In a negatively curved universe, k is less than 0. To better understand elliptical and hyperbolic geometry, check out the book by Professor Hitchman I will include in the description section below. Each of these shapes can also be described by the universe's density. Critical density is the density of matter required for the universe to just barely stop expansion. In a flat space, the universe's density equals the critical density. Omega, the ratio of the density of the universe over the critical density, is equal to 1. If the density of the universe is greater than the critical density, the universe is a positively curved closed space. Rho universe is greater than rho critical, so omega is greater than 1. If the density of the universe is less than the critical density, the universe is a negatively curved open space. Rho universe is less than rho critical, so omega is less than 1. As far as we know, the universe is flat. Research to date, including observations from the Atacama Cosmology Telescope, NASA's Wilkinson Microwave Anisotropy Probe, and the European Space Agency's Planck spacecraft, has shown that the universe, as far as we can see, has essentially no curvature, with only a 0.4% margin of error. This could mean that the universe only appears flat in our region of space and perhaps begins to show signs of curvature farther out. But for now, the general consensus is that the universe is flat, while a few scientists continue to explore other options. Well, that's all for now. Thanks for watching, and as always, ponder, wonder, and go right in the stars.
Slow motion, yeah. I feel like an astronaut in the ocean. Like, what you know